Alright, this is the notes for section 9.3, continuous compounding. If you could take a few minutes right now, in your book there's an activity, and I have kind of in your notes a place for you to fill this in. I'd like you to just go through, please, and see if you can fill in this chart. And I want you to really pay attention to what's happening over here in this A column in terms of where that number is kind of ending up when we get down to the daily, hourly, by the minute. It's going to lead to a number that's somewhat similar to pi. So if you could do that at this time, and then I'm going to put the answers up to that so you can check it, and then we'll talk about it from there. Alright, so here's the answers to that activity, and you'll notice that as the number of periods increases earlier, so if I go from 1 to 2, in other words, I've doubled the number of periods. Okay, I've added one extra period, I've doubled the number of periods, and there's a pretty significant difference in the amounts here, going from $2 to $2.25. However, as I move further down the chart, when I'm going from 8,760 compoundings to 525,600 compoundings, so that's quite a big difference. It's a huge difference, almost well, enormous, relatively speaking. But yet the amount of money in terms of difference, it's very, very minute. We're going from, if I look at the last three numbers, 813 to 828, so very, very, very small change in the value. So it appears that as the number of the periods gets bigger and bigger and bigger, the number that the amount is approaching is one particular number. Okay, and that one particular number is what we call E. Okay, so the activity leads to Euler's number, which we call E, and E is this number, 2.718, blah 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 blah. It's just like pi, and then it's non-terminating, non-repeating decimal that will keep going forever, and it represents this. It represents the value of $1 after 1 year invested at 100% interest, compounded continuously. Okay, so by knowing that value, by knowing about Euler's number, it's something that we can use so that we can actually convert or calculate interest on a continuous basis. And actually we can apply it to any type of growth or decay that is a continuous situation. Okay, so let's look at the continuously compounded interest formula, and that just says if an amount P is invested in an account paying an annual interest rate of R, compounded continuously, the amount in the account after T years is A equals PE to the RT. So just like we had before, we had our, and we were working with interest formulas before, we had our amount, we had our principal, but instead of 1 plus the rate raised to the time, we're now going to say we're going to take E, that 100%, $1 compounded at 100% interest continuously. We're going to take that number and raise it to the rate times the time. Okay, so A equals PE to the RT. I'm going to erase this so you can still see the formula there. So A equals PE to the RT. Let's take a look at example 1 then. It says Mona invested $8,218.16 in a zero coupon bond paying 4.5% compounded semi-annually. After 25 years, the value of the bond will be about $25,000. How much would Mona's investment have been worth after 25 years if the interest were compounded continuously instead of twice per year? Okay. So to do this problem, I don't need to know about what a zero coupon bond is. That really doesn't matter. What I do want to do is I want to find out. I know that after 25 years, it's worth $25,000, and she put an initial amount of 82,1816 into the bond. So and we know it was compounded at a 4.5%. So what I want to do is figure out, well, how much would she have if it were compounded continuously? So I'm going to use my formula, A equals P E to the RT. Okay? So I'm going to say the amount, which is what I don't know, is equal to the principal, which started as the same amount, 82,1816, times E, and I just leave that as the number E. We can just write it just like that, raised to the RT. Well, the R was 4.5%, so it's going to be 0.045 times T, which in this case is times 25. So all I'm going to do is I'm going to use my calculator to do those calculations at this time. So in my calculator I'm going to enter that in, 82,1816 times. Now to get e to the x, you have an e to the x button right here on your calculator. If you click on that, it will bring in the value of e, and it will write it as e, but it will calculate it in that 2.71, just like pi does. And then I'm going to raise this to the 0.045, I believe that was, times 25. Oops. Okay. And we're going to go ahead and calculate that then. So if I go ahead and enter this, I get $25,313.71. So that would be the value of the bond, just a little bit more, about $313, $314 more if it was compounded continuously instead of semi-annually. So there's where I have that value in there, $25,313.71. So the number E can be used in a lot of continuous growth situations. So many formulas will use E in them because the exponential function y equals e to the x has some properties that are very suitable to a lot of applications. So let's take a look at an example of one of those. It says the amount L of a certain radioactive substance remaining after T years decreases according to the formula L equals BE to the negative 0.0001 T, where B is the initial amount of radioactive substance. If 2,000 grams are left after 6,000 years, how many grams were present initially? Okay. Well, then the amount of grams that are present initially is B. So what we're doing here is we're going to solve this equation here for B. So I'm going to plug in what I know. I know that L is 2,000. That's how much I have left right now. B I don't know. And then I have E to the negative 0.0001, and then T is the number of years. It says substance remaining after T years. Well, it says 2,000 grams are left after 6,000 years, so this is 6,000 for T. Okay, so remember, E is not a variable here. E is still a number about 2.71. So we have all numbers except for B, so it is something that we can solve for. Now before I go to my calculator, I'm just going to solve this for B. So if I divide both sides by E to the negative 0.0001 times 6,000, if I do that, I'll have what B is. So this is what I'm going to put in my calculator, the stuff on the left. This cancels out, so B is equal to that. So let's go ahead and put that in our calculator and see what the value would be for B. So if I enter that, if I have 2,000 over E to the negative, now the calculator automatically did this, but you can just enter in 0.0001 times 6,000. If I do that, I get 3,644.23, so about 3,644 grams. So the amount that I would have there for B would be about 3,644 grams. So this would be the answer if we solve that for B.